Okay, recording part 2 here. So we're doing example 3. We've got our setup. We've integrated this. We have our boundaries that go from lower boundary of 0 up to a higher boundary of 2. And now we can just simply plug in our numbers. So if we take 2 times 2 cubed, which is 2 times 8, that's our 16. And then we take 2 and square it and multiply it by a 3. So we're looking at 12 over 2, which is 6. 2 times 2 is 4. We will subtract. And now 0, you're going to get to know this right there. He will now be your new best friend. You think you have a best friend at Avon High School, right? Maybe it's your boyfriend, maybe it's your girlfriend, maybe it's just a really close friend that you have. They are not your best friend. 0 is now going to be your best friend because he's so easy to work with when you're evaluating the fundamental theorem. So now we just simply have 16 over 3 minus 2, which is the same as 16 minus 6, I guess. So we end up with 10/3. Okay, now I am going to share something else with you guys. I'm going to switch over to my wonderful graphing calculator. Maybe if I could find it. Well, that's interesting. It's like it doesn't want to show up. And all right, maybe I'm not going to show you that. Okay. For whatever reason, it's not wanting to show up on my options, and I think it's just because I've put this computer through heck. This is my 3rd Zoom session today, so I apologize for any things that are going on. But in any event, I was going to sketch this graph. All I remember is that it looks a little something like, well, it's a parabola, right? It's a parabola, and I think it has some stuff that lies below the x-axis. Maybe, I don't know. But anyhow, what we were able to do is we were able to find the area underneath this parabola. Maybe it lies all above the x-axis, in fact. And we can't use geometry because, indeed, it is a parabola, and that's the problem that we're faced with. So anyhow, 10/3 is our answer, and if you guys want to see graphical evidence of this, you would just simply have to type this into your own calculator. Okay, now what we are going to do here is of huge monumental importance. This is one of the most important things in the entire course that I'm going to show you, and it just so happens to land on an e-learning day. So we're going to investigate this thing called the mean value theorem for integrals. And it just simply, uses some common things that we've seen, a definite integral from a to b of the function f of x, and then it's got this weird little stuff here to the right, which we may not be able to relate to so much just yet. So what I'm going to have you guys do, if you want to make your notes look like my notes, is I'm going to take this left graph, and about the 3rd mark over, I'm going to put an a there, and maybe the 3rd mark from the right, I'll put a b there. It really doesn't matter if you put your a and the b in the same spot. It might be nice if you guys can look at a graph that's the same as mine, and I'm going to do the same thing for the right side graph. All right. Now, I want to just make up some generic function f of x on the left side. And you don't have to draw it in the exact same location, but if you can make it look a little bit like this graph, it will be a little helpful. It's just an increasing graph that changes from concave down, up to concave down. And we can kind of bring him on down to B and A. And then if you want, you can take your pencil or pen or crayon or writing utensil of choice, and you can color underneath that graph. There we go. Pretty little yellow right there. Yeah. Okay. All right, I'll give you guys a few more seconds to finish that up. And my hope is that I can get you guys all convinced that if I'm calling this graph f of x, and that's who he is, then this yellow shaded region has the value that's equivalent to that definite integral. I don't think anybody's going to have a hard time believing that, right? That's what we've learned, right? That's what the definite integral means. It is the area under a curve between two bend points. But the tricky thing is, what is this right side stuff? What does all of this mean? And we have this introduction of C. There exists a number C. Well, if you drew the graph somewhat like mine, I think the C value is pretty much halfway between A and B, pretty close perhaps. So maybe we can put a C somewhere, it's probably a little farther over. Maybe we can put a C somewhere in that vicinity. And obviously there would be an F of C. But what I want to do is sort of carry that value over, if I could, to the right graph. And by the time I get to that same height between A and B, I'm going to draw that in, bring them down to the A and the B, and I have, guess what? I have a rectangle, good job, and I'm going to shade him. And I'm very, very, very picky about what I want to shade him in, and I'm going to use yellow. Now, why again would I use yellow? Because I want you guys to know that these are the same value, that the area underneath the curvy thing on the left is the same as the area of this rectangular thing on the right. It's probably not too far-fetched if you think about that left side again, and that this rectangle that I just drew on the right side sort of misses out on that shape, but it brings in this area that we didn't want, and those could seemingly cancel each other out. Okay, if you're thinking that this reminds you a little bit of the midpoint approximation, that's okay to think that, but this is actually going to go somewhere completely different. Okay, it's not really this theorem that's the important thing. It's what I'm about to show you on the next slide. It's what this results in. That's just huge. All I want you to get from this slide is that there is a way that you can take this irregular shape and sort of like pretend it was like a piece of clay and sort of reform it into a rectangle that would have the same exact area. What becomes very powerful is if you go to this equation that you see right up here and take this F of C and get him all by himself. That would be done by dividing the B minus A over, right? Well, if we do that, you have, and then you can kind of look at this. This is actually, I think you have to, you have this all on your same page of notes. You then have the average value of a function. So if you want, you could think of all of this as being set equal to F of C. Okay, not that I wrote the F of C there. I didn't really think I needed it, but this expression, this absolute, this definite integral A to B, the thing that we've been playing around with for the last couple of days, coupled with the 1 over B minus A in front, has this new special meaning called the average value of a function. Okay, big deal. So what? What does that mean? Well, if we go up to that previous picture, you have just figured out a way to find the average value along this curve f of x. And I'm not talking about some weird version of average. I'm talking about the old school average. I'm talking about adding all of these y values up and dividing them. So how many y values would you say are on this curve f of x? How many of them are there? Let's add them all up, shall we? Well, that could be interesting, right? Because there are actually an infinite number of them, right? So we are taking the infinite number of these y values, adding them all together, and then we're going to divide by how many y values we see, which is, guess what? Infinity, and we can get an answer. So we can now take some really crazy curve and figure out, on average, how tall it is, how far it is from the x-axis. Mathematically, that's somewhat interesting. The math geeks out there might think it's cool, but for those of you who want a little bit more application, whether you are a science-oriented person, a social studies-oriented person, or even, say, a business-oriented person, there are ramifications of this average value in all of those fields. We have a graph of income. What is our average income? We have a graph of the average population of this population of elk in this wildlife preserve. We can find the average, right? It just extends on and on. So it's pretty cool. It's pretty powerful. And you know what else is cool about it, guys? It's really easy because it's just taking the definite integral that you're already getting pretty good at and putting this 1 over b minus a in front of it. So when it says here in example 4, hey, let's find the average value of this function, then we're just going to say, okay, we start with the 1 over b minus a. Got that done first, right? Using our a and b that's given. And then we just throw our integral down, you know? We just do what we've been doing already in the first part of this unit or this section. Okay, so we'll finish this up. This gives us 1/3. And the integration of 3x squared is going to be x cubed. And the integration of 2x is x squared. So you really had some very nice, easy ones here. And then we have our boundaries 4 to 1. And then we will plug in our boundaries 4 and 1. So, oh, don't have my best friend. But you know, 4 and 1's okay. One's not my best friend, but he's a pretty close ally. You know, I don't mind working with 1. I'll trust my innermost secrets to 1. So we're going to plug 4 in, and we're going to get 64 minus 16 minus, and then when we plug 1 in, 1 really helps us out there, right? 1 minus 1. And then I think we've got 1/3 times 48. So the answer is 16. I meant for this to be a pretty nice value. Okay. Let's see. Lexi, excellent question. Why is there no 3? Call this my fault. I think I may have tried to do this a little too fast. If we integrate 3x squared, we would have 3x cubed all over 3, right? I just went ahead and canceled the 3's. And I guess you could say I did the same thing for the 2x. This is really 2x squared all over 2. Okay, so I apologize that, and it's very likely that some other people may have been confused by that. All right, and great job. Anytime that you guys have a question, throw it in the chat because I've got it scrolling across my screen and I will see it right away. Okay, and if by some chance you have a question that's really hard to type, just in the chat, just say, can I ask a question or something, and I'll just go ahead and unmute you if you've got a microphone. All right, so we can definitely do that as well. All right, I'm checking on something here. I'm checking to see. See, now I can share my calculator. Wow, weird. Okay, and the reason why I wanted to do this is just to give you a chance to kind of like let your hand rest if you've been taking notes fast and furiously, but also to graph this particular guy, to graph this 3x squared minus 2x. You can follow along. You don't need to get your calculator out. And then I'm going to have to play around with this a little bit because I don't think I like its window size. So I'm going to change this to like -2. I may have to go up as high as maybe 50. I'll explain why. And I can take this guy out, well, maybe as long as I go out farther than 4. 5 will work. And then maybe I'll take this guy out to -2. Yeah, that'll work. Okay, now I need to go into my menu and then basically fix all that stuff by changing my scales accordingly. X scale at 1 would be fine. Y scale, oh boy, you guess. Your guess is as good as mine. You know what? I'm gonna live life on the wild side. I'm gonna go 5. Yeah, sometimes you just have to do that. Okay. Now I'm going to put grid lines in, and I'm going to warn you these grids probably won't look square because of my scale is all kind of weird. But what I wanted to kind of demonstrate to you is that if I were analyzing this function right here that I'm trying to move from x = 1 to x = 4, the average height of it, the average y that I would have would be about 16, and 16 would occur probably right about where my the tip of the index finger is of that open hand. Remember that each grid is 5 units along the y-axis. So this would be about the average height of that function, okay, which is pretty important. Now, if I return back to the notes page, which should now be shared with you, we're going to move on to part B, which is kind of a funny thing to me, because normally my students don't struggle much at all with part A of these kinds of questions. And that's good because you will see them a ton, okay? But part B kind of gives kids problems. And everybody needs to say kind of like an imaginary hi to Katie. Katie Stegman, she's kind of hanging out with the AB group because she had so much fun this morning with the BC Zoom session. Am I right, Katie? Is that why you're here? All right. So for part B, we're going to go ahead and find the value of C guaranteed by the mean value theorem. Now, when kids see this question, they really start to panic and freak out because they think, I've got to do something so crazy different. And the fact is you don't. And the fact is, I don't even think this is a calculus question, because they're just saying, hey, you've got that function f of x, right? We just graphed it. We saw it. We know what it looks like. It's blue. That's why I'm using blue to write it up. I want to know, for what x value does that guy achieve that average value that we found? So that's all you do. You just set the original function equal to your answer from part A. Okay, now I know it asks you to find the value of C. I don't have C in the problem. X, C are really the same thing. I mean, if you want to change all this and change the X's to C's, that's fine. But if you look at the top of your page, you see, I'm going to get rid of all this writing. Basically, you're just solving that variable for this equation now, and you've done all the dirty work over here on the left side. Okay, so all you got to be able to do to solve this equation is pretty much like know how to factor, you know. So I'm going to subtract the 16 over to the right, or from the right, and basically I'm going to cross my fingers and say, does this factor? Remember my rule about factoring? If you can't factor this in 30 seconds, then just go ahead and use the quadratic formula. So, 4 and 4, I don't know. Is that going to work? I don't like that. 8 and 2, does 8 and 2 have a chance? 8 and 2 has a good chance, doesn't it? I think that's going to do it, isn't it? Because if we make this 8x minus and the 6x positive, we've got the minus 2x that we need. So I think that we were able to do this well within our 30-second time limit, and we end up getting these two results. Okay, does that seem good so far? And again, feel free to just type a question in the chat if you've got any issue, or just say stop. All right, so we've got this information. What is our final answer? Can we just like circle the answer choice that has both of these? And the answer is no. What we have to do is understand that between 1 and 4, that's all that we care about. That's where our answers have to lie. So if you think about the old mean value theorem, Rolle's theorem, stuff that we learned in the first semester where you had to kind of pay attention to the interval, that's coming back now. Obviously, -2 does not lie in that interval. So we have to toss it away, and only x equal 8/3 will be our answer. Okay, so make sure that you're very, very cognizant of that. Got a question. Why does the 8 and 2 work? Why does the 8 and 2 work? I thought that the numbers had to add up to the -2x in the middle. Oh, because of the 3. I think the 3 is going to cause a lot of issues there because we don't have a just a single 1 coefficient. So you have to check these more so by foiling than just by relying on, does 8 and 2 add or subtract to 2 or -2? Does that make sense? Does that make sense? Okay. Can we only factor out x in the equation equal to 0. The problem with that, if you factor out an x, these are good questions, you guys. A lot of students want to do this, and then they just say, okay, that means that x is, I guess you would assume that x is 16 or 3x plus 2 is 16, I guess, and then go to solve. I don't know. But the problem is there's no property that says that that's true. If you assume this, you're saying that you have two numbers multiplied by each other that have to equal 16. You're saying that one of those numbers has to be 16. And that's not true because 8 and 2 work, right? 4 and 4 work. So there's this thing called the zero product property. And sometimes we lose sight of that's its name, and it's called that for a reason. And that's why all of our equations that are to higher powers have to be set equal 0. You can't solve, guys, you can't solve squares and cubes in equations unless you set them equal to 0. Because here, when you have two numbers multiplied by each other, you know that one of them has to be 0. You have no doubt that that's the case anymore. So we set both of them equal to 0. Okay? All right. Hopefully that makes a little sense. If I were to share my calculator page one more time here, kind of revisit him, we just discovered that when x is 8/3, which is 2 2/3, right? So what would you guys say? That's right about here, about where my arrow is. It says that the y value there would be 16, and I would say that that's probably true. Okay, I could do a point on feature if I had my geometry option available, but geometry is not an option unless we're in a document. Now, if I want to make this a document, it's pretty darn easy. I just basically say, okay, let's save this as a document, right? So I could just say Control Save, make this a new document. Guess what? It's now a document, right? Which means if I go to Menu, I've got this cool option called Geometry, and I could put a point on the curve, and then I can move it around. And I bet if we get there somewhere in the vicinity, 8/3, which is what, 2.6 repeating. Now it's going to be virtually impossible to get that right on. It's probably as close as I can get there. So hopefully you trust that is that point. Okay. The calculator doesn't have a feature that will find the average value of the function, right? I mean, if you had a very difficult one, I suppose you could use the calculator to do the integration for you. So, all right, I'm going to share back to the document, and we are going to move on to our wonderful example 5, which is our first real-world application of fundamental theorem. Okay, sorry, I had to eat a chip. All right, so we have example 5, and in example 5, it says that oil is leaking from a storage tank, and it's doing so at this rate given by this expression R of t. So we know that negative t squared over 12 plus 100 is this rate, and we want to kind of say this to ourselves over and over again. From this point on, guys, a lot of times I'm going to give you some function. The AP exam is notorious for this, and that function will be a rate. It may not look like a rate. It may not have a prime mark attached to it. It may not have d over dt or d over dx attached to it, but it will be a rate because it'll say it's a rate. Plus, the label might give it away too, that that's a rate. Okay? Now, part A is kind of the tedious part of this, especially in terms of trying to teach this through Zoom, but we're going to make this work for us. It says to graph the curve on the coordinate plane. So I'll tell you what I'm going to do. I'll do all the calculator work, and then I'll let you guys just kind of like transfer it to your page. Okay, so what do I mean by that? I'm going to go to my calculator, and I'm going to tell you what I'm going to do. You know what I'm going to do? I'm going to make a new page because I'm in a document now, right? So I can go Control Doc, add a page, and how about a graph page, right? So I'm about to graph this. What fun, right? Now, the graph that I'm going to type in, the equation, is going to be the one that you've got. However, I'm not going to get kind of cute or anything and change the variable from x to a t. We really can't do that very well on the Inspire. So I'm going to go ahead and make this negative quantity x squared, or negative x squared over 12 plus 100. All right, and we just have to understand that the x is playing the role of t, and f2 of x is our r of t. Now, when I hit enter, you're going to be disappointed. Are you ready to get royally disappointed? I'm disappointed. I don't see anything. And the reason I don't see anything is because I don't think this window is large enough. So what I'm going to do to change this window is go into menu, change the window settings, and I'm just going to go with the settings that I see right there on my notes page. You guys see your notes in front of you. Hopefully you can kind of come to the realization that the boxes along the x-axis, I think, have a units of 1. I mean, if you want to count all the way over there to 20, you're welcome to do that. I want you to keep in mind that that 20 is the very far right edge of the graph, and the 200 would be the very, very top. So that being said, I think -3 as a min, 20 as a max, and a scale of 1 is spot on, right? Now for the y's, it's a little bit trickier because do I not have the calculator screen up? Are you guys seeing what I'm saying? Do you see what you don't see what I see? Dang it. All right. Now you see what I see. Okay, I'm with you guys. I'm with you. I just diverted my attention from the chat for 2 minutes, and look what happens. All heck breaks out. But anyhow, guys, hopefully this is okay. I tried to sketch the graph, and nothing was showing up, so I'm just changing the window size. Okay, just changing the window size. So my y min, would you guys be okay if I went with what, -10, and the y max would be 200? Because is it a safe assumption that the scale is 10? Is the scale 10 along the y-axis, I think? We're good, aren't we? So let's go ahead and hit OK for all this. Hit OK. Hey, I see a graph, right? I see a graph. I'm excited about that. We see this graph, finally. Okay. Part of the reason why I miss you guys on chat is because I have 15 windows open on my computer, and I have to move things around, and you don't see anything except what I'm sharing. But okay, so we see the graph, and I think now if you want, I could put in some window grid lines, might help a bit. But to be honest, if you guys are like looking at this thinking, yeah, I have to like copy this to my paper, kind of a pain, isn't it? Let's be honest, it's a big pain. So what I might suggest is I'll help you out. I'll help you out by putting a table, Control-T. Okay, well, maybe that helps a wee bit, but we can't really see the table so nicely. So I'll do my little magic trick. I'll do Control-6. Control-6 is awesome because that will put the table on its separate page 1-4. Now I can maybe scroll through this, and I'll just give you guys like about 10 seconds to do each set of 5 points. And I know that initially you're like, what? I don't see my y values changing very much from being much less than 100, right? And I get that. So you're really just plotting some points that almost look like horizontal lines, right? But I'll let you go ahead and do that, and then I'll kind of gradually scroll. Meanwhile, I will nibble on my Nacho Bel Grande. Because when you're doing Zoom sessions all morning, there's no time for lunch. I know that, I mean, by the time you get to 15, 81 is not all that far from where 100 is it? And you can actually stop right here at the 20. When you get to the far right of the graph, you're only at 66 2/3, okay? Does anybody need me to scroll back up for any of these points? Because I'd be happy to do that. I'll be happy to do that. And I'll show you the graph again on the calculator. And basically, it'd be nice if you have your graph on paper that looks close to it. I'm going to do something kind of cool here. I'm going to switch the view back to the notes, but I'm going to bring the calculator in to the notes a little bit. All right, so hopefully this will work. Kids, don't try this at home. Don't try this at home. There we go. Actually, you can try this at home. Just don't do what I did because that was dumb. I need to bring in not the table, but the graph. So hold on here. I just need to, there's the graph, right? So, hey, I could just cheat. I could just do this. Hey, I got it sketched. Looks pretty good. Yeah. So as long as your graph looks something like that, everything is good to go. Okay. Everything's good to go. Okay. And the thing that I just did is kind of cool. You guys can do that. If you bought a TI Inspire and you have the student software that comes with many of the packages, you just grab a piece of the screen when you have the software, and you can grab a graph and you can move it into a Word document. You can move it into a PowerPoint. You can move any kind of calculator screen into pretty much any program. And you might think, well, why would I want to do that? Well, that could be a cool thing for like a lab report or something. So if anybody has any questions about that, just holler and I can help you with that if you ever need to do that before you leave Avon High School. So we've got part A done. How about we take a look at part B, which part B and C and D will take a lot less time than part A did altogether. How much oil leaked out by the end of the 5th day, right? So that's the same question as how many wings did El Wingador consume, right? We're looking for the total amount, so we can do this wonderful, wonderful thing called integrating the rate. So if we integrate the rate, we will get the total amount, just as long as we use the correct boundaries. They went by the end of the 5th day, so that means we would start at 0 because we start right when the oil is spilt, and then we end at 5, which would be basically midnight on the 5th day. And that would span the 5 days. You could have written out the entire expression if you wanted to instead of the RFT, but the AP exam, as well as myself, will always accept a function name. I like that for 2 reasons. A, it's quicker to write. It's usually shorter. And B, there's always a chance that if you copy this down, you could make a mistake, mess up a sign or something, and now you won't do that because you've given him his name RFT. All right? We could integrate this by hand, but let's be honest, we've pretty much compromised every principle that's in our body up to this point. Excuse me, by using the calculator. So why don't we go ahead and use the calculator to do this? So I'm going to remember to share the calculator screen again. And on this calculator screen, I'm just going to make another page. And I'll make this a calculator page. And we are going to integrate. We're going to do our good old friend Shift plus, and we're going to integrate from 0 to 5. Now let's be straight up here. If we try to like type in R of T, yeah, good luck with that, right? Because the calculator doesn't understand what R of T is. It's not like there was some magical communication going on between your calculator and your notes packet right now, right? That'd be cool. That will probably happen in the year 2029, but that's not happening right now. So what we're going to do is we're going to refer back to what was that function's name? Oh, I remember it was f2 of x. So if we call this f2 of x, we don't have to type in that expression. And I want you to know that that's a feature that spans both the document and the Scratchpad. So if you were just doing this in a Scratchpad graph page and a Scratchpad calculator page are in sync with each other. They are communicating basically, okay? Now I'm probably guessing this is going to give me an ugly or a fractional answer, which is possible, which means nobody talks like that. You know, how much oil is leaked out? Oh, well, that's how much oil, 17,000 over 36. Nope. So what we'll do is we'll hit Control Enter to give us a decimal approximation. So that's what we're going to go with. Okay. So Double checking, making sure everything's going all right. Got that calculator problem number, that calculator answer, 496.528. So now I'm going to share this again. 496. Didn't say to round any certain way, did it? I mean, I guess we just have to put everything in there. 528. I guess we're getting kind of nitpicky about this answer, but let's not make up any rounding rules. Let's go ahead and practice rounding to 3 places. Now, next thing up, I'm going to let this kind of open up to the chat. If you guys want to do the chat, it's another kind of cheap way for me to take a bite of my Nacho Bel Grande. What's the label? What is the label for this answer? Who could be the first one to give me a label? They will win a prize. Grant Landis. And our Katie Stegman, or is it really Katie Stegman? Good job, Julie. Good job. 3000352. Good job. That's awesome. Your prize is one of my nachos, and I'll save them for you. Okay? So we definitely want to make sure that we put the correct label there. Okay, now. Oh, okay, I get it. Okay, so for part C, how much oil has leaked out between the 5th and the 10th day? Well, you guys are going to do something very similar, something very, very similar here. You're going to go ahead and use the definite integration. I tried to give you a little hint as to what the boundaries are going to be, because some kids overthink it and they think, oh, wait a minute, this is a trick question. Between the 5th and the 10th, would that be like starting on the 6th day and you go from 6 to 10? But that's not true. You guys, if you start with the number 5 in the lower boundary, that would start the 6th day. And if you have a hard time believing that, basically think about, how old are you when you're 3 months old? That's a dumb question. I'm 3 months, right? Well, no, how many years old are you? Well, you're still technically 0, right? You're not 1 year old until your first birthday. So when we start here at 5, we have entered our 6th day. That's the way to think about that. So don't overthink that. Not that many of you thought it would be anything different than 5 to 10. So this is what we're looking for, right? So again, I got to remember to switch back and forth. Holler at me if I forget to do that. So if I go back to the calculator, I'm going to make this really easy, and I'm going to go up here and copy and paste this. And I'm going to change this guy to 10. I'm going to change this guy not to 5, but I'm going to put a decimal so I don't have to mess with that control enter anymore. And then I get 475.694. 475.694. I'm going to share the other page. 479. Is that what it was? I have such terrible short-term memory. 475.694. Got the 9 and the 5 mixed up. 475.694. Thank you. Thank you, Jake. So that's our answer. We are asked, why is that answer less in part A? Well, you could write a novel if you wanted to, but it's not really necessary. Basically, you can just refer to the behavior of the graph. And I probably do want to put the label in here. That would be very wise. And the reason is really because f of x is doing something. F of x is, or r of t is, the function, it's decreasing. I mean, I think that's really the only thing that you have to state. This rate is decreasing, so we ought to have less gallons leaked out during the same time interval, okay? And maybe we add that. R of t is decreasing, and our 2 time intervals are the same length. Our 2 time intervals have equal lengths. And I'm just going to abbreviate so that we can get through this quickly, okay? Now, when you get to question D, this is where all of the Environmental Protection Agency people are coming onto the scene. They're all kind of, angry. Just like those movies that you see whenever like the people that are really in charge, they show up and they just yell a lot, right? And they don't really do anything to fix the problem. So we got these people showing up and they're like, all right, well, I want to know, what is the average daily loss? All right, that's what I'm concerned about over the 20 days. What's that bottom line? Well, you got this word average, right? The word average. They basically want to know, what is the average value of this RFT function over 0 to 20. So this is where all the magical stuff that we just taught comes into play. You've got 1 over 20 minus 0, integrate from 0 to 20 of the RFT expression with respect to t. Okay? And again, we've been using the calculator over and over and over, so we're not going to stop now. So if I go back to the calculator here, I will now cheat, go up and copy this guy here. I'm going to make sure that I put a 1 over 20 minus 0 in front. I guess I don't really need the 0 so much, but what the heck. And I'll put a 0 here and a 20 up there, and that should give me the average value of the RFT, and it's 88.888 or 889. And before I get the entire chat yelling at me, label, label, I'm going to ask you guys, what will this label be? Think carefully. Haven't heard it yet. I think you guys are kind of thinking about this, and that's good. Okay. I think we got it. I think we have a winner, 3000352. It is gallons per day. Gallons per day. It's not just gallons anymore, because this guy here was gallons, but we've got this new sort of denominator in town, right? This 20 minus 0, 20 days minus 0 days. So there's another like day in the denominator, okay? So average value of a function will always retain the same label that the function had. Does that make sense? And you don't ever want to forget that, because that'll follow you. Wow, this problem was so fun. I wish there was a part E, but there's not. So here's what we're going to do, guys. I want to go ahead and show you this, the second fundamental theorem, because if I do, you're going to be right on track with the timeline, and you're going to be in really good shape. And plus, this is really quick and easy to show you. And that will also put you guys ahead of period 3, which I'll have to kind of work to get them caught up a little bit tomorrow. But I won't necessarily have to do that with you guys, which is going to be really nice. If we don't get, by some chance, the ability to get through all 10 problems by the end of the week, rather than force that upon Mrs. Ryan to teach you and show you, I will just make videos of anything that I don't get finished, and you guys can maybe watch those through the weekend as you guys get ready for the exam midway, or as you guys get ready to start the last section, and then the exam isn't until the very, very following week. So you've got some time, and I think that'll work out well. The reason I say that is I have no idea what's happening tomorrow. I've heard rumors of a 2-hour delay. Don't quote me on that. I've also heard that it's probably all systems go for a normal day. I don't think we're going to have another whole day off for e-learning, though, because the temperatures are going to break a little bit. Okay, so the quiz over this section 4.4 will be on Monday. All right, and the reason is because you're going to have a good question and answer time that you can use on Friday with Mrs. Ryan. And I know she's going to do a good job with it. She's got all of this material. She's tutored this and taught this many times. She's not going to lead you astray. All right, so we'll be okay for the quiz on Monday. All right, and if you guys have a lot of anxiety about this, just come in on Monday morning and I can kind of work with you if you need help. And if you need to ask a question or two before the quiz, even in class, we can make that happen. Okay, Sean, not too much longer. Not too much longer. I tried to shoot for an hour, and we're going to be pretty close to that. All right, so I am going to share with you back to the notes. Okay, so we have this idea called the second fundamental theorem, and it says we've got the definite integral as a number. Okay, that's interesting. And then over here we have the definite integral as a function of x. Okay, so what's up with that? Well, just so you know, it is possible to do some really weird things to these. Instead of putting this upper boundary as a numerical quantity, we could put the upper boundary as some unknown value. Maybe we don't know how far to go up from 0. Maybe we want to figure out what that needs to be in order for something to happen. Well, the only way that this will make sense, you guys, is to use some other letter of the alphabet in those two spots. And you don't really typically see X used there again. Luckily, you've got like 25 other choices besides X, and T seems to be a nice default. But when all is said and done, it's important to understand that this is a function of X. Because if we were to integrate this f of t, sure, it would be an expression that probably has t's in it. But as soon as you evaluate from x to 0, won't those t's get replaced by x's? And then the t's replaced by zeros, and then you would likely have a function that only has x in it. And I hope that makes a little bit of sense, because sometimes students get confused a bit about the t and the x. All right, but now the question is why? What is this? Well, this is going to lead us to what's called the fundamental theorem part 2, or the second fundamental theorem. And it just simply says, if you ever have this kind of integration with the unknown upper boundary, as long as the lower boundary is a constant, it does not have to be 0. The lower boundary just has to be a constant. There are times that we find that we want to take the derivative of this. Well, that seems kind of weird. You're taking a derivative of an integral? Wouldn't those cancel each other out? Well, you tell me, isn't that what happened? They do cancel each other out. Now, what you get isn't f of t, but it's f of x. It's f of x. You want to know the super shortcut? Take the upper boundary, replace the t in the expression, and you've got your answer. And that's all there is to the second fundamental theorem. So these last few examples, you guys, are going to go super fast. We're just going to do example 6 and 7, and then we'll call it a day. So for problem 6, evaluate this. Well, you remember that shortcut I just showed you? Let's pretend that I forgot that, all right? You know me, I'm notorious for not showing you shortcuts all the time, showing you long ways. That's okay. Let's do this the longer way, and I want you to follow along with me. Put this longer way in your notes. If we were to take this integration, t squared plus 1, we would get t cubed over 3 plus t, and we would have to evaluate that from x down to 0, right? And then we'll worry about taking the derivative later. So meanwhile, this derivative is sitting and waiting very patiently. We replace the t's with x's. We see our best friend is here. And then we take the derivative of what's left. The derivative of x cubed over 3 is x squared, right? Is that agreeable? X squared. The derivative of x is 1, and boom, you have your answer. But do you all see that we could have had that answer much faster if we just replaced the t's with x? It's that simple. So, what is the answer to B? Probably type this in the chat if you wanted to. You don't have to, but if anybody wanted to, you're welcome. Like Ahmed and Jose are quick to the draw there. They did a good job. And that's exactly it. 5x minus 3, you just replace the t with the x. Okay, you replace the t with the x. This denominator here, Lexi, what happened was when I took the derivative, the 3 comes out in front, right? And then I have this x cubed that turns into x squared. And then that 3 in the denominator just has to plop down, but it cancels with that 3. Okay, so again, I just took the derivative without showing a step. All right. Okay. The box for the second fundamental theorem had an A where the 0 would be. So yes, good, Sean. This is just to illustrate that this example, even though this had a 0 and this had a 2, it makes no difference. That number could have been 28, and the answer is still the same. Now, if anybody's like, why is that? Why is that the case? Well, it doesn't matter, what this number is, because if this is integrated and you plug in that number for those t's, you're going to get a number. Isn't the next step taking the derivative? And the derivative of a number is going to make it go away anyway. So when that lower boundary is a constant, it's pretty easy. Now, if that lower boundary is something besides a constant, it's also very easy, and we'll talk about that in a moment. Okay? So what do we do about example 7? Well, in this example, I could type this into the calculator, and usually that's what I do with students, but with you guys, I'm going to kind of explain what would happen. If I type this into the calculator, it will give the right answer, but it's not what you would expect. In other words, if you're thinking, is this 5x squared plus 1? There's more to it than that. Even though there's still this constant in the bottom, there's more to it than that. Now, why is there more to it? Well, let me show you down below, and you can choose to write this or not. It's not very long. But if I went the long way with example A, the derivative would sit and wait patiently. I would integrate t plus 1. And then expect to evaluate it along those boundaries. Okay, so far so good. Now, when we plug in the boundaries, 5x squared plugs in for the t, and that's kind of tricky. I'd have to square everything, and I would get 25x to the 4th, I believe, over 2. And then, of course, add 5x squared. Okay? And then I would subtract 0. I would subtract 0. 0 is our best friend, right? But now we are obligated to finish the problem by taking the derivative. So the 4 comes in front, cancels with the 2. So I guess I could write that as 2 times, and then I would have 25x cubed, right? Hopefully everybody follows that. Basically, it's 4 over 2, 25x to the 3rd. And then that's an easy derivative, 10x. So when all is said and done, the answer should be 50x cubed plus 10x. 50x cubed plus 10x. But if we look up here at our answer in red, we don't have anything that's nearly as robust as that. It seems like there's something more that we need to tack onto this. Maybe something more that we need to multiply this by. Maybe we need to multiply it by the derivative of that upper bound. Do these match, guys? They do now. So the trick is the chain rule. If you have an upper boundary that's more than just an x, you have to go ahead, plug him into the t like you normally would, but then follow up by multiplying by his derivative. Okay, now if you distribute it through, that's okay. If you leave it factored, that's okay. Okay, now if we look back at example 6, obviously that never had to happen, because the derivative of each of these the upper boundaries was just going to be a 1. So you have to really be on your toes for that. So to do part B, I got 2 things working here. The first one is, okay, the upper boundary is more than just an x, right? So we would have to replace all of the t's with 2x cubed. Okay, did that, but we learned our lesson in that all of this would have to be multiplied by the derivative, or 6x squared. So far, so good? But I got a feeling some of you are like, wait, lower boundary x, lower boundary x. Well, guys, this does not happen very often. But if it does, do the same thing with the lower boundary that you would with the top boundary. You would plug it in for the t. And then remember, this is all about the fundamental theorem. So what sign do you think goes here? Would we add, subtract, multiply, divide? What does the fundamental theorem say to do? It's subtract. Yeah. Now, if that's the case, I probably ought to advise us to put that in parentheses. And then, you guys, I'm going to do something weird here. I don't want this to confuse you, but if you want to multiply by 1 to kind of say, hey, everything's a chain rule, you are welcome to do that. Okay. This thing could be simplified a little bit, and maybe, you know, it could have this look to it. There's a variety of ways that you could write it. We could even distribute this in further. But I know that you will be very good at being able to match it on multiple choice. And quite frankly, on a free response, I've got like 8 different things that I would accept, and they're all full credit. So hopefully that makes sense. And guys, that's it. That's that fundamental theorem part 2 that I was really eager to get through today. And I know it took us a little bit, 5 minutes over, but that should take care of you. I think you guys are going to be able to get through all of the homework that was on the timeline. I'm kind of reaching around my kitchen table here, and I'm going to grab my homework binder just to kind of verify how far. Oh my gosh, I just got Nacho Bel Grande cheese all over my cord, mouse, and mouse pad. See what I do for you guys? Wow, it is a sight. So I'm looking at 4.4b, and you guys are in good shape to get all the way through problem 6. Problem 6. That's where you're using the second fundamental theorem in those 4 little parts, A, B, C, and D. So all should be pretty good. All should be good except for the fact that I don't have a napkin. But hey, I'll make do. Anybody have, oh, period 7 does not have the 4.4b worksheet. Wow. Wow, somebody got to fire me. Well, I'm going to share Schoology here with you guys if you want. You know where to find it, I'm sure, but hopefully you can all see the Schoology screen. If you go into period 7, I'm looking for a second here. Whoops, nope, not there. That's not what I want to do. And if I go into that Unit 8 folder and go into the homework worksheets, homework 4.4b, what I wanted to do, guys, I wanted to check and make sure it was a PDF file, because if it was just a Word, weird things could happen too. So both period 4 and period 7, you guys are probably going to want to print this out. I'm sorry. I didn't think about that, because that's the only way that you're going to really be able to get a head start on this. So if you wouldn't mind doing that, that would be awesome. If by some chance you have printer issues at home, or you're out of ink or whatever, I'm sure that you could work some problems on a separate sheet and just kind of call this up. But you'll get a copy of it tomorrow, I guess. If you really feel like you can make a lot of progress tomorrow and get after this tomorrow night in time to really be able to answer questions to Mrs. Ryan, that's okay. The key is by Friday or by Monday, you want to have it done so that you're ready for the quiz. All right, so I'll let you guys decide. If you want to start it tonight, print it out. If you want to just wait tomorrow, that's fine. If by some weird occurrence that we are on a, another e-learning day tomorrow, I'll set up another Zoom session because you guys have class tomorrow, and then you pretty much have no choice but to have to acquire it, print it out, or start working it off on a separate sheet of paper. So, all right, so you'll get it tomorrow if that's your plan and if we have school. So yeah, that's one thing I didn't think about, old e-learning. So anybody else have any other questions? Okay, all right. Sean, have fun with that bee swarm simulator. I'm sure that's a blast. All right. Hopefully your e-learning day is kind of drawing to a close and you guys can relax, have a little fun, watch some Netflix, go outside and play in the dangerously freezing wind chill temperatures. So, but if nobody has any issues, I'm gonna shut down, and I'm gonna try to start things saving so I can maybe post these to people who weren't here, and that's where the time really starts to kind of accumulate for an e-learning day for me as a teacher. So all right. So good luck, and looks like tomorrow, if all goes well, I will see all of you because we do have class on Thursday. So all right, take care, guys.